Every single day, millions of people reach for this exact product, expecting a flawless, completely identical sensory experience. This disposable sheet is actually a highly engineered microscopic cellulose matrix. For millennia, civilizations have sought inventive solutions for hygiene. By the 2nd century AD, the Chinese were cutting large sheets of newly invented paper into smaller, scented squares reserved for the elite. The modern commercial industry grew out of World War I. Manufacturers developed a creped cellulose wadding as a substitute for cotton surgical bandages, then repurposed the absorbent material in 1924 as a disposable makeup remover. This item is the physical manifestation of centuries of shifting societal standards for comfort and cleanliness. The engineering begins with a paradox. The paper is specifically designed for structural failure. It relies on a network of hydrogen bonds that provide tensile strength when dry, but are designed to release their grip the moment the fibers are saturated in water. Yet before it reaches the consumer, the web must survive a violent, high-speed manufacturing environment and remain perfectly intact. This delicate balance is further complicated by the source material. The softest tissue grades originate from rigid, unyielding wood. Solving this structural contradiction requires an orchestrated application of physics and chemistry on an industrial scale. Inside the modern tissue megafactory, every environment is dedicated to the limits of tensile engineering. The journey starts in chemical digesters, where wood chips are subjected to intense thermal shock to dissolve the lignin that gives trees their rigid strength. This process isolates the pure cellulose fibers, transforming them into a chaotic liquid slurry that is 99.5% water. This slurry is blasted onto a moving micromesh screen, where massive industrial vacuums instantly rip the water away. This rapid extraction forces the microscopic fibers to naturally lock together through millions of invisible hydrogen bonds, forming a solid but temporary web. Extracting the liquid in a fraction of a second is the essential mechanism that transforms a chaotic fluid into a cohesive, delicate solid. The wet web is then plastered onto a steam-heated Yankee cylinder, where it is flash-boiled dry in milliseconds. Because untreated cellulose dries stiff and rough, it requires a violent mechanical intervention to create plushness. The stiff, dry paper hits a razor-sharp titanium creping blade at speeds over 5,000 feet per minute. This creates a continuous competition of fracture mechanics. An interfacial crack propagates through the adhesive layer, creating a delamination length. The sheet eventually buckles and collapses, arresting the crack to form a physical crepe fold hundreds of times a second. This precise, high-speed structural sabotage is the sole reason the rigid paper feels soft and luxurious. Mechanical creping has a limit. If the blade fractures the paper too aggressively, the tissue will disintegrate on the production line. To add surface luxury without losing strength, factories apply topical wet-end softeners and lotions. In the electrostatic application method, high voltage is used to generate tiny droplets that migrate onto the sheet in a perfectly controlled coat. This chemical microcoating achieves a velvet feel while preserving the fiber matrix's fundamental absorbency. During quality control, high-resolution optical scanners evaluate the topographical consistency of the moving web. To ensure effective hygiene, the fiber matrix must possess the exact porosity required for rapid capillary action. Any roll that fails to absorb fluid instantly without catastrophic structural failure is rejected and dissolved back into pulp. Approved rolls move to the packaging phase, where orbital saws slice massive tissue logs at speeds faster than the human eye can track. Mechanical fingers compress and wrap the rolls in ultra-thin plastic. This wrapping creates a specific exterior tension, acting as a final structural component that protects the sensitive microcrepes from crushing during global transit. The sheer volume of this operation is staggering. A single machine can output thousands of feet of paper every minute. The result is a perfect harmony of fluid dynamics, of mechanical fracturing, and industrial robotics. A violent process of boiling and shredding wood has been beautifully tamed into a weightless, cloud-like geometry. Every sheet pulled from the box represents a single day's production, long enough to wrap around the Earth. all while maintaining the exact same microscopic absorbency.